is a little bit of stuff about pizza. If you get a small pizza, it's all right. It might feed maybe one of my boys if they're not feeling especially hungry. You get a medium pizza, it's quite a bit more pizza. Then you get a large pizza, it might not even be that far further in diameter, but it's a lot more pizza. All right, I get a medium one for my kids, I'll eat that thing, no problem. I get a large, it'll feed both of them. A little bit in the slice left over for my wife. Now I got about 2 larges. Where the other one? All right, and then so what we find is the same effect. When we spread out, we have more room for these fancier pictures. So when I'm real close to the nucleus, on that first energy level, I only have room for the S. And when I get a little bit further out, I got room for the S and the P. And what we're going to do is, it's an easy pattern. Every time I add a row, I'm going to add a column. So I'll have the 3S, 3P. What's next? 3D. And 4S and 4P and 4D and 4F. 5S and 5P, 5D, 5F and 5G. 6S and 6P, 6D, and all of a sudden I quit writing them nice. I don't know why. 6G, 6H. I was worried about running off to the edge. Ah, they can't even see the H. Hit it. You guys can't even see the H. I hit it. Go. And so we could keep taking this as far down as we want. So the book's always trying to stop these at 7. Take them down further. That's the beauty of this system. Once we know the pattern, we build it. All right. So we're ready to do electron configurations. And why we do these electron configurations. So an electron config is to avoid having to give all the information that quantum numbers give. If I'm trying to tell you where the quantum numbers are, oh, let's do beryllium. It's got 4 electrons. I'd have to list out the quantum numbers, and I have to run through all those little rules in my head. And so I'm going to be doing n equal to 1, L equal to 0, M equal to 0, S equal to 1/2. N equal to 1, L equal to 0, M equal to 0, S equal to -1/2. Lithium, or the third electron would be N equal to 2, L equal to 0, M equal to 0, S is -1/2. N equal to 2, L equal to 0, M equal to 0, S is minus, let's see, that do plus 1/2. The opposite one I did. That's just 4. Can you imagine what happens when I get to bromine and I got 35? Or I'm walking out of a full parking lot and you're pulling into it and you say, Dr. J, did you see any spots? I said, yes, I did. Go, sweet. I go, well, the first row, the first spot had a car in it. The first row, the second spot had a car in it. The first row, the third spot had a car. You gonna stick around and listen till you find that spot? No. So electron configuration is a nice way to get an idea of where's the empty spots. So we use stuff that looks like this. Turn lights back on for me. One will end it in the goodness. Here's n is equal to 1. That's what that big 1 is telling. What is that S telling me? It's telling me that L is equal to 0. What's it telling me when I see a P? Oops. L equals 1. So I started 0 and I counted by 1. Okay? All right. So up here, this tells me my number of electrons. Got 2 up there. So why did we have to use this special letters? Why didn't I just write this L n equal to 1 and L equal to 0? Well, if you saw this on the page, would you know what it was? It looks like 10 squared, right? Yeah, so that's why we had to switch over to using letters. So the L values are based off of numbers, but we've got letters for them. We're going to focus on the letters. Now, this is only helpful to me if I know how many fit in the S's. How many does each S hold? 2. And so this is saying, hey, this first S is full. And the second S is full. Okay? Is this P full? No. How many can it hold? 6. And this guy only got 3 in. So the next electron I add would go in those P's. That's what we use electron configurations for. Now we run into a little bit of problem in that these pictures over here are too simple. Particularly that sphere. It looks like a nice, empty kind of sphere, but it's actually, if I were to draw it, it's got like a little inside fuzzy part. Somewhere on that inside. And the math works out to be, it's hard, really hard to draw, because how are you going to draw a 2-layer sphere, right? So if I look at a cross section, in other words, I'm going across like that, I'm going to see, so if it was just an empty sphere, like this picture looks like, we'd see something like this. You have a sharp peak when you got to that layer. Kind of like, think of a tennis ball. You ever cut open a tennis ball or let your dog chew it open, whatever? It's empty on the inside, then it's thick, and then it's gone, right? But what we actually see for the S's is more of a little hump, and then we get our peak. There we go. This little hump is going to cause us some troubles. And those troubles, talk about right here, are called, this little hump here, cause of this is called electron tunneling. And it gives us a problem of these electrons having different energies than what we would expect. Because what would make sense to us would be we fill up the 1s, then we'd fill up the 2s, and then the 2p, and the 3, and then we'd just kind of go across. And when I got to the 3ds, then the 4s, and the 4p, and the 4d. But nature doesn't do that. And so our job is not to tell nature what to do, it's to describe what's going on. And so the picture that kind of helps us with that is, I think it should be the next picture. Picture looks like this, which I'm sure they can't see online. But, so if I'm going, energy is kind of how close it is to the nucleus, and it's going to feel from the lowest energy first. All right? So what's first? 1s. Got to speak up because they can't see this. So 1s, all right, then what? Then 2s, then what? 2p is going to be lower, and there's 3 of those, right? So it can hold 6. Each one of these is an orbital, right? And then what's next? The 3s, good. The 3p, and we've got 3 of those. We'll fill those up. And then what's next? 4s is next. It's lower than the 3d. Why is it lower? Because it's got that inside part. These were close enough in energy that that little inside part kicked it down in lower energy. That's electron tunneling. So we got to be able to predict what we see in nature from this on our graph down, on our little chart down here. So here's how we do it. This is why I left the light on so we can do this. I'm going to draw this arrows I'm going to try and keep them parallel. And it's going to go through here. And this tells me my filling order. And the way you do this is old good old number 1 right here. And we're going to start right here. And we go, and then when I fall off, it wraps around to the next one. When I fall off, it'll wrap around to the next one. Okay. So if I follow the arrows here, I'm going to get the 1S, then the 2S, then the 2P, and the 3S. That's still just like we see before. But now we explain we're doing 3P, then the 4S, then we'll hit the 3D, and I can even say the next one should be 4P. What you did. You can even use these to do your electron configurations. And I see people use this all the time. And they'll come in and they'll put a big number 2 and a 6 and a 10. And I'm not even going to bother doing it because I've got those numbers up here. We got them in that table. We know that all the S's hold how many? 2. And all the P's hold 6. All right, so here we go. We're going to show you how this method works. It's a bicycle method. I don't want you doing it this way. All right, I don't want you doing this, but the way it works is you figure out which one's next, you figure out how many it holds, and you figure out how many electrons you have. You do it over and over and over. And it's okay, but it's slow. It'll eventually get you there. But there's a better method. The better method we're going to use is based off of the off-ball principle. The off-ball principle says that if you go forward a box on the periodic table, you add an electron. Now I thought, okay, yeah, that's easy enough. I wish I'd come up with that. When I was a student, I was like, man, that's easy. You can really get that named. What I didn't realize is we've drawn the modern periodic table so that it's easy to use this principle. So it didn't used to look like this. Didn't always, so it wasn't such a real simple principle. This is designed with his principle in mind. All right, so here's my periodic table. If we did it this way, I had a student one time ask me, if I know how to do this, why do I gotta learn this other way? I was like, this will eventually get you there. It's like riding a bicycle. It'll get you there. If you're going a long way, though, it's going to take you a while. You're never going to finish this test. Compared to that, this method's like driving a Ferrari. All right? So I'm going to teach you how to drive a Ferrari. Now, the first step in driving a Ferrari is to watch somebody else drive a Ferrari. And that somebody else can't ever help but show off. So this first one, don't try to write it down. Just get an idea of what's happening. All right? It's going to seem like a lot, but it's okay. Let's do, I don't care, let's do bromine. And I picked that one earlier as an example of worst case scenario if I was doing quantum numbers, right? So bromine, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5.